Hello students, welcome to my YouTube channel, and today we are going to start a new chapter, Semiconductor Devices. So this chapter is very important for the students, those who study physics in class 12th, as well as for the students of first year of electrical engineering and electronics engineering. So what is the purpose of studying the semiconductor devices? So in modern technology nowadays, the use of chips, the nano chips and the chips, microchips which are using the semiconductor devices are frequent. So it's very necessary to study the semiconductor devices in detail. So in this topic, basically we will study the basic concepts of semiconductor devices. So let's start the discussion. So first we are going to classify uh, insulator, conductor and semiconductors. So in this topic, first we are going to see the classification. So first we are going to see the classification of conductors, semiconductors and insulator. Semiconductor and insulator. So basically first we will see the classification of semiconductor, conductor and insulator. So the basis of classification, basically there are two bases of classification of semiconductor, insulator and conductor. The first basis is on the basis of conductivity. So the first classification we will see on the basis of conductivity. So on the basis of conductivity, or we can say resistivity. Reciprocal of conductivity is known as resistivity. And the second basis of classification of conductor, semiconductor and insulator is based upon on the basis of energy band. On the basis of energy bands. So this is our discussion on the basis of energy bands. So first we are going to see the classification of conductor, semiconductor and insulator on the basis of conductivity, or we can say resistivity. Basis of conductivity and resistivity. So first we are going to see the classification of conductors, insulators and semiconductor on the basis of conductivity. So on the basis of conductivity, we represent by the symbol sigma, or resistivity. The reciprocal of conductivity is known as resistivity. Both are reciprocal of each other. Rho. And resistivity is the reciprocal of conductivity, 1 upon sigma. So the first classification, the first basis of classification of conductors, semiconductors and insulator on the basis of conductivity or resistivity. So let's see. So let me make a column here. We are going to form a column here. Let me classify conductors, semiconductors and insulators. So first we are going to see is conductors. Conductors. Next is semiconductors, semiconductor, and last one is insulator. So in case of semiconductor, basically metals or semiconductors, they possess very low resistivity or high conductivity. So conductors they possess very low resistivity, and if the resistivity is very low, then its conductivity is very high, or we can say high conductivity. So conductors, their value of resistivity is very low, but the conductivity of conductors are very high. The typical value of resistivity of conductors is 10 to the power minus 2 to 10 to the power minus 8 ohm meter. This is the value of resistivity. The value is very low, and the value of resistivity, just take the reciprocal, it will be equal to 10 to the power 2 to 10 to the power 8 Siemens meter inverse. This is the value of resistivity and conductivity for the conductors. For semiconductors, their resistivity and conductivity is intermediate to the conductors and insulators. So first let me see the insulators first. So basically insulators have very high resistivity and or we can say or low conductivity. Their value of resistivity is very high, but the conductivity is very low. The value is basically the value of resistivity is very high, 10 to the power 11 to 10 to the power 19 ohm meter, and the value of conductivity for insulators is very low. It is 10 to the power minus 11 to 10 to the power minus 19 Siemens meter inverse. This is the value of the resistivity and conductivity for the insulators. Their resistivity value is very high, but their conductivity value is very low. Coming to the semiconductors. So the value of resistivity as well as the conductivity for semiconductor, the value lies between the values of conductors and insulators. Basically, semiconductors have got the properties intermediate to the properties of conductors and insulators. So they have resistivity or conductivity. Semiconductors, they have resistivity or conductivity intermediate to conductors and insulators. Now the value of resistivity for semiconductors is basically 10 to the power minus 5 low to high, 10 to the power 6 ohm meter, and the value of resistivity, it's very high, 10 to the power 5 to low, not very high, it is intermediate, 10 to the power 5 to very low value, intermediate value, 10 to the power minus 6 Siemens meter inverse. So this is the classification of conductors, insulators, and semiconductors on the basis of their conductivity and resistivity. So when we discuss or when we classify conductors, semiconductors, and insulator on the basis of their conductivity, we find that in case of conductors, the value of resistivity is very low and the conductivity is very high. The value is given. And similarly, for case of insulators, the value of resistivity is very high, but the conductivity is very low. And in case of semiconductors, the value of resistivity and conductivity lies between that of the conductors and insulator. So this is one of the basis of classification of conductors, semiconductors, and insulators. Now the second basis of classification is based upon the energy bands. So now we are going to classify the conductors, insulators, and semiconductors on the basis of energy band. So on the basis of energy band, how we can classify energy band, how we can classify semiconductor, insulators and conductors. So let me discuss some important term here, then we will go into the classification of conductors, semiconductors and insulator. First is the energy band. So what is energy band? Energy band. So it is nothing but when we discuss about the electrons, so each electron, each electron inside a crystal, inside a crystal have different energy levels, energy levels with continuous energy variations, energy variations, which is known as, which is known as energy bands, energy bands. So when we discuss about the electron, because when we discuss about the atomic structure of an element, we find that electrons, protons and neutrons are there. Protons and neutrons resides inside the nucleus, and the electrons are revolving around positively charged nucleus in a fixed orbit, and each orbit have got the fixed energy. Suppose this is the atomic structure, this is the positively charged nucleus, and around this positively charged nucleus, if you are considering the circular orbits, these are the orbits. In this orbit, electrons are revolving around this positively charged nucleus. Then we find that all the electrons have different energy in these orbits. The energy is basically fixed in this orbit, and we find that there is a continuous variation. Suppose energy of this first orbit is E1, energy of second orbit is E2, and this energy of third orbit is E3. All these energy are continuously changing. Okay, each electron have fixed energy. So, or we can say different energy. This E1 is different, E1, E2, and similarly E3. All these energy are different. All the electrons, electrons in first orbit, electron in second orbit, electron in third orbit, all have different energy levels. E1, E2, and E3, they are known as energy levels. Energy levels. Energy levels. So basically each electron, when electron is present in a lattice, then all the electrons have different energy levels with continuous energy variations. This energy is continuously varying. It is not concentrated at a single point. The energy is continuously varying, which is known as energy band. And this continuous variation of energy in a lattice of an electron, that is known as energy band. Now after energy band, we are going to the next term that we are going to see in this energy band. The next term is valence band, VB. We can call valence band, valence band. Suppose I'm writing valence band by VB. So valence band, what is valence band? The energy inside a inside a crystal, basically the energy which includes, basically we can write down, basically we are writing the definition of energy band here. So the energy which includes the energy of the valence electrons. So the energy which includes the energy levels of the valence electrons, the valence electrons are known as energy band are known as energy band. So this is the definition all about the energy band. Now next is your conduction band. After valence band, we have conduction band, conduction band. We write conduction band by CB. So the energy band above, the energy band above valence band, valence band is known as conduction band. So basically, in energy bands, we can classify the energy band of the electrons. One is known as valence band, the electrons which are present in the valence shell of a lattice or valence shell of any element, then they will have the energy also. So the variation of energy of the electrons in valence band, that is known as valence band simply. And conduction band, the energy above the energy band above the valence band, that is known as conduction band. So the basic definition, conduction band. And next is the energy band gap. Like we have the energy difference between these two cells, that is E1 minus E2. Between these two cells, between 2 and 3, it is E2 minus E3. So similarly, there will be some difference of energy in case of valence band and conduction band. It may be zero also. So next is the energy band gap. Energy band gap. It is represented by, suppose, symbol Eg. Then the gap between, this is defined as the gap between top of the valence band, top of the valence band and bottom of the conduction band, conduction band is called the energy band gap, the energy band gap. So these are the three definitions we must remember when we are going to discuss the classification of conductors, semiconductors and insulators on the basis of energy band diagram or energy band. So energy band is nothing but the continuous variation of energy of the electrons inside a crystal is known as energy band. Now valence band includes the energy of the valence electrons and the conduction band includes the energy of the conduction electrons or the energy above the valence band, that is known as conduction band. And the difference of energy levels between valence band and conduction band, it is known as energy band gap. So these are the three definitions just we have seen. Now we are going to classify conductors, semiconductors and insulators. So first I am going to draw energy band diagram of the conductors. First I am going to discuss the energy band diagram of the conductors. First let me draw the energy band. So first I am going to discuss the energy band diagram of conductors. So this is our conduction band and we have another band. This is our valence band and both are overlapping. You can see it there. Okay, now let me define the bands. First, this band is known as conduction band CB and this band is valence band. Both the bands are overlapping. You can easily see that the electrons which are present in valence shell, they are also available for conduction in the conduction band also, because this is your conduction band. These are the electrons, suppose you are representing, we are representing. So we can easily see that at room temperature the electrons are already available in valence band. There is no any difference. this energy gap, the top we are taking top of valence band. So suppose energy I am writing EV, and this is the bottom of conduction band EC. Both are overlapping, you can clearly see that. So the energy gap between these two bands EG, it is equal to 0. There is no any energy gap between the conduction band and valence band. If you will move from valence band to, suppose we are drawing the graph, when we are moving from valence band to conduction band, the energy is increasing. Okay, this is showing you the variation of the energy from conduction band to, from valence band to conduction band. So in this direction, the energy levels of the free electrons, we can say energy levels of the electrons in this direction, it is increasing. Then in case of conductors, we can easily see that the conduction band and the valence band both are overlapping. Here you can see it there, overlapping. Conduction band CB and VB, CB and VB are overlapping, due to which there is no any difference of energy between conduction band and valence band. That's why in case of conductors, the electrons are easily available for the conduction, or electrons are available free to take part in the conduction inside a conductor. Now we are moving to the next band diagram, that is energy band diagram of the semiconductors. Now we are going to draw. So next diagram is for, we are going to draw the energy band diagram for the semiconductors. Semiconductors. This is the energy band diagram. Energy band diagram. Now we are going to discuss the energy band diagram of the semiconductors. So let me draw the bands first, conduction band and valence band. So this is representing the conduction band, and this part it is representing the valence band, suppose. You can easily see that. This is our conduction band CB, and this is your valence band. In valence band, electrons are present there, and the energy of these electrons is nothing but the energy of valence band. These are the electrons present in the valence cell. So the energy of these electrons is known as the valence band, and this is your conduction band. Now when we are moving from bottom to top, from bottom to top, from valence band to conduction band, the electron energy is increasing. The energy of the electron is increasing in this direction. It is giving you the electron energy. Energy of the electron is increasing from valence band to conduction band. This is the bottom of the valence band. Let me take the difference of the energy. This is the top of the valence band. I am writing the energy of this band as EV, and this is the bottom of conduction band. I am writing the energy of this bottom level by EC, and the difference of energy between these two levels, basically this difference is known as energy gap or energy band gap, we call it. So EG, the difference of energy between the bottom of valence band and the top of the conduction band, it is EG, energy gap, and this energy gap is less than 3 electron volt. So at room temperature we can easily see that there is no any electron present in the conduction band. That's why semiconductor does not conduct at room temperature. But when we supply the energy, thermal energy, or from the energy we are supplying to this semiconductor from outside, the electrons will absorb energy and they will get excited. If that, because the difference of energy between the conduction band and the valence band is very less, 3 electron volt only, less than 3 electron volt only, so we can supply the energy of the photon, or energy of the radiation or heat energy we can supply. Then electrons will absorb this energy and get excited, and they may jump from conduction, from valence band to conduction band. And once the electrons will be available in the valence conduction band, they are or they are available for taking part in the conduction. The electrons may jump, okay, from valence band to conduction band, because the energy difference between the conduction band and valence band is very low if it is thermally excited. These electrons, when they are thermally excited, they can jump from valence band to conduction band, and this way the semiconductor will start conducting. So at room temperature, generally there is no any electron present in the conduction band, but if we are able to supply the energy, because the difference of energy between conduction band and valence band is very low, so if you are able to supply the energy, thermal energy, the electrons may excite from valence band to conduction band, and this semiconductor will start conducting. So this is all about the energy band diagram of the semiconductors. Now moving next to the topic, the energy band diagram of insulators. Now we are going to draw the energy band diagram of insulators. So suppose this is representing the conduction band, valence band, conduction band, and this part it is representing the valence band. This is representing the conduction band. From conduction band to valence band, the electron energy is increasing, and this is the difference of energy between the conduction band and valence band. So basically this is representing conduction band CB, and this is representing valence band VV, and this is the top of the valence band energy. Suppose I am writing by EV, energy of the electrons, and bottom of the conduction band we are writing AC. The difference of energy between these two levels, it is known as energy gap EG, and this EG is basically greater than 3 electron volt. It's very high value is there, more than 3 electron volt. It's a high value. So generally electrons are present in the outermost cell of the outermost cell. These are the electrons which are valence electrons. At room temperature the insulator does not conduct because they don't have any electron in the conduction band. Now suppose we are supplying the energy from outside, then these electrons will absorb the energy and will get excited. But due to the large difference of energy between the conduction band and valence band, these electrons cannot jump from valence band to conduction band. Cannot jump these electrons because the difference of energy between conduction band and valence band is very high. If the electrons are thermally excited also, then that's why insulator does not conduct even if we are supplying its thermal energy to the insulators. So this is all about the energy band diagram of the conductors, insulators and semiconductors. So what we have seen, for conductors, just we have seen for conductors the difference of energy between the conduction band and valence band, it is equal to 0. That's why conductors easily conduct when we apply the electric field. For semiconductors, there is some difference of energy between conduction band and valence band, and this energy gap is less than 3 electron volt. So generally at room temperature semiconductor does not conduct, but when we supply the thermal energy, the electrons will get excited and they will jump from valence band to conduction band and they can conduct. And for insulators, the difference of energy between conduction band and valence band, it is high, that is greater than 3 electron volt. That's why insulator does not conduct. So this is all about the energy band diagram of the semiconductors, conductors and insulators. Now we are moving to the next topic now. So this is the classification of the semiconductors on the basis of their conductivity and on the basis of energy band diagram. Now let's see one more classification of the semiconductors. So we are going to classify semiconductors. Now semiconductors can be classified into two categories. One is known as elemental semiconductor and other is known as compound semiconductor. Now we can easily classify. Semiconductors can be classified into two categories first. One is known as elemental semiconductor. One is known as elemental semiconductor or pure semiconductor, we can call it elemental semiconductor. Examples are silicon and germanium. These are the pure semiconductor or elemental semiconductor. And second one is compound semiconductor, having some impurity in the elemental semiconductor. We are getting compound semiconductor. Now compound semiconductor, again they are classified into three categories. Let me classify this. They are classified into three categories. One, two, and three. Now compound semiconductors are classified into three categories. One is known as inorganic semiconductors. The first is inorganic compound semiconductors. So in inorganic, we have the examples CDS, cadmium sulfide, then gallium arsenide, GaAs. These are the examples of inorganic compound semiconductors. These are the examples of inorganic compound semiconductors. Next is the organic. Inorganic semiconductors, these are the examples: anthracene, and doped thylocyanines, and doped cyanines. And in case of, and last is the organic polymers. Organic polymers. So the first example of organic polymer is polypyrrole. Polypyrrole, then polyaniline. These are the examples of compound semiconductors. Now, so semiconductors can be classified into two categories. One is known as elemental semiconductor or pure semiconductor, we can call it. Other is compound semiconductor. When we are adding some impurity to the elemental semiconductor, the semiconductor will become a compound semiconductor. Now, compound semiconductors are classified into three categories. One is inorganic, second is organic, and third is organic polymers.